Hello students, today's lecture is the concluding part of classification of elements and periodicity in properties. In today's discussions, we will discuss about periodic trends in chemical properties, revision of Unit 3, previous year's questions and exemplars. This is a very important point. Please listen to my lecture very carefully and note down all the important points. Before proceeding further, we will just recap what we have learned in Unit 3. The periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electron negativity, and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increase across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies in general become more negative across a period and less negative down a group. So we will continue further. Periodicity of valence or oxidation state. The valence is the most characteristic property of elements and can be understood in terms of their electronic configurations. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and are equal to 8 minus the number of outermost electrons as shown in the table above. So the table shows the group, first group, second group, 13, 14, 15, 16, 17 and 18. So the number of valence electrons are 1, 2, 3, etc. up to 8 respectively. And the valence is, corresponding valence is 1, 2, 3, 4, 3 and 5, 2, 6, 1, 7, 0, 8. The term oxidation state is frequently used for valence. So we use the term oxidation state for valence. The oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. So oxidation state can be defined as the charge acquired by its atoms on the basis of electronegative consideration from the other atoms in the molecule. Some periodic trends observed in the valence elements, that is hydrides and oxides, are shown in this table. This is the table 2. There are many elements which exhibit variable valence. So the first row is groups 1, 2, 3, 14, 15, 16, 17, and the second row is formula of hydride. You can see here LiH, NaH, KH, etc. and for respective groups. And similarly, the formula for oxide is also shown in the table. Please pause this video and go through each and every element and observe the formulae of hydride and oxides. Let us solve one simple problem. Using the periodic table, predict the formulae of compounds which might be formed by following pairs of elements. Number 1 is silicon and bromine and aluminum and sulfur. Answer. Silicon is a group 14 element. See here, silicon falls in the group 14. See Si, its hydride is SiH4 and its valence is 4 as shown in this green colored table. Bromine belongs to the halogen family with a valence of 1. Hence, the formula of compound formed would be SiBr4. Part B. Aluminum belongs to 13th group 13, with a valence of 3. Group 13 and valence of 3. Sulfur belongs to group 16, group 16 and valence of 2. Hence, the formula for aluminum would be Al2S3. Anomalous properties of second period elements. The first element of the groups 1, that is lithium, 2 beryllium, and groups 13 to 17, that is boron to fluorine, differ in many respects from the other members of their respective group. So I repeat, the first element of each of the group 1, that is lithium, and group 2 beryllium, and groups 13 to 17 boron to fluorine differs in many respects from other members of their respective groups. These are shown in the table on the screen. The behavior of lithium and beryllium is more similar with the second element of the following group. So, second element of the following group is magnesium and aluminum, second and third. Magnesium respectively. This sort of similarity is commonly referred to as diagonal relation. Please read this sentence once again. The behavior of lithium and beryllium is more similar with the second element of the following group, that is group here, following group, that is magnesium and aluminum respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties. The anomalous behavior is attributed to the small size, large charge/radius ratio and high electronegativity of the elements. Let us take one simple problem question. Question number 2. Are the oxidation state and covalency of aluminum in the compound AlClH2O5 to the power of 2 plus same? Answer is no. The oxidation state of aluminum is plus 3 and covalency is 6. Periodic trends and chemical reactivity. The chemical reactivity is high at two extremes and lowest in the center. In the periodic table, if you observe, the chemical reactivity is high at the two extremes of the table and the lowest in the center. The maximum chemical reactivity at the extreme left, that is among alkali metals, is exhibited by loss of an electron leading to the formation of cations, and at the extreme right, that is among halogen, shown by the gain of electron forming an anion. The metallic characters of an element which is highest at the extremely left decreases and non-metallic character increases while moving from left to right across the period. The metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing properties. The chemical reactivity of an element can be best shown by its reaction with the oxygen and halogens. Consider the reaction of elements with oxygen only. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on the extreme left is most basic, example Na2O, whereas that formed by the element on the extreme right is the most acidic. Please remember, the normal oxide formed by the element on the extreme left is most basic, that is Na2O, whereas formed by the element in the extreme right is the most acidic. For example, Cl2O7. Oxides of elements in the center are amphoteric. Example, Al2O3, As2O3, are neutral. Example, CONO, N2O. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas neutral oxides have no acidic or basic properties. Among transition metals, that is 3D series, the change in atomic radii is much smaller as compared to those of the representative elements across the period. The change in atomic radii is still smaller among inner transition metals, that is 4F series. The ionization enthalpies are intermediate between those of S and P blocks, and they are less electropositive than group 1 and group 2 metals. Let us take one question. Question number 3. Show by a chemical reaction with water that Na2O is basic oxide and Cl2O7 is an acidic oxide. Answer: Na2O with water forms a strong base, whereas Cl2O7 forms a strong acid. For example, we can write the equation: Na2O combines with water to form 2NaOH. Similarly, Cl2O7 combines with water to form 2HClO4. Their basic or acidic nature can be qualitatively tested with litmus paper. Thus, in a group, the increase in the atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease, with exception some third period elements, in electron gain enthalpy in the case of main group elements. Thus, the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property, which we will see later. In the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization therapy. Let us summarize what we have learned in Unit 3. In this unit, we have studied the development of periodic law and periodic table. We have also studied Mendeleev's periodic table, which was based on the atomic masses. Modern periodic table arranges elements in the order of their atomic numbers in 7 horizontal rows, that is periods, and 18 vertical columns called groups or families. Atomic numbers in a period are consecutive, whereas in a group they increase in a pattern. Elements of the same group have similar valence shell electronic configuration and therefore exhibit similar chemical properties. Please read once again. The elements of the same group have similar valence shell electronic configuration and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right and therefore have different valencies. Four types of elements can be recognized in a periodic table on the basis of their electronic configurations. These are S block, P block, D block and F block elements. Hydrogen with one electron in the 1s orbital occupies a unique position in the periodic table. Metals comprise more than 78% of the known elements. Non-metals, which are located at the top of the periodic table, are less than 20 in numbers. Elements which lie at the border between the metals and non-metals, example silicon, germanium, arsenic, As, are called metalloids or semi-metals. Metallic character increases with increasing atomic number in a group, whereas it decreases from left to right in a period. The physical and chemical properties of elements vary periodically with atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, and electronegativity and valence. The atomic radii decrease while going from left to right in a period and increase with an atomic number in a group. Ionization enthalpies generally increase across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies in general become more negative across a period and less negative down a group. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity. Chemical reactivity is highest at the two extremes of the period and is lowest at the center. The reactivity on the left extreme of a period is because of the ease of electron loss or low ionization enthalpy. Highly reactive elements do not occur in nature in free state. They usually occur in combined form. Oxides formed of the elements on the left are basic and the elements on the right are acidic. So please remember, oxides formed of the elements on the left are basic and on the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral. Now we will take up some previous year's questions. Question number 1. Identify the incorrect match. So the table in the blue color shows the name of the element and its corresponding IUPAC official name. In this table, some incorrect match is also given. You have to remember and answer it correctly. So the correct answer, that is incorrect match, you have to identify. Option A is B, 2, option B is C, 3, option C is D, 4, and option D is A, 1. So this is the, here answers are given and you have to identify which is incorrect in this table. So you please pause the video and write your answer. Meanwhile, I will explain. Unonium Z is equal to 111 is Roentgenium. This is shown in the table as in the column 1 as option D. And it is shown as option, it is given the option as Darmstadtium. So this is D is match as 4. It is a wrong match. So you have to mark it. Correct answer is, so this is the incorrect match is D, 4. This is incorrect match. It should have been Roentgenium. Next question. Match the following. So here two columns are given. Oxides are given CO, BaO, Al2O3, Cl2O7. And here also in the right side it is basic, neutral, acidic and amphoteric. So you have to match. So there are 4 options A, B, C, D. These are given in the columns and their corresponding matches are given here. You have to match. That is A is 2, B is 1, C is 4, D is 4, etc. etc. You have to match it correctly. So now I will explain it. CO is a neutral oxide. BaO is a basic. So CO should be matched with neutral. That is CO should go to match with 2. That is A should go with 2. So here only this column is the correct. A appears to be correct. And BaO is a neutral, is a basic oxide. Basic. So B option B should be 1. So the correct choice will be A. Please mark it. Next question. The element Z is equal to 114 has been discovered recently. It will belong to which of the following family? So carbon family, oxygen family, nitrogen family and halogen family are shown. And their electronic configurations are also given as option A, option B, option C and option D. So you have to mark the answer correctly. So you have to identify where Z it belongs to. So after Rn group 18, elements form atomic number 89 to 103. That is actinides are in group 3. And 114, that is 103 plus 11. Thus, the element with atomic number 114 will be group 3 plus 11 or group 14. That is carbon family. So, option A will be the correct answer. Please mark it. The outer shell configuration of group 14 is Ns square equals Np square. Next question. An atom has electronic configuration 1s square, 2s square, 2p6, 3s square, 3p6, 3d cube, 4s square. You will place it in which group? Read the question once again. An atom has electronic configuration of first period s square, second period 2s square, second period once again 2s square and 2p6, and third period 3s square and 3p6 and 3d cube, and fourth is 4s square, fourth period. You will place it in which group? This is the question. So four options are given. Fifth, option A is fifth, option B is 15th, and option C is second, and option D is third. Please pause the video and mark your correct answer. The electronic configuration clearly suggests that it is a D block element having configuration n-1, D to the power of 1 to 10, and n s0-2, which starts 0 to 2, which starts from group 3 and goes till group 12. Hence, with D3 configuration, it will be classified in the fifth group. So option A, mark it, and that is the correct answer. The element with atomic number 118 will be whether option A, whether it is alkali, whether or a noble gas, option C, lanthanide, and option D, transition element. Electronic configuration of element with atomic number 118 will be 5f14, 6d10, 7s square and 7p6. Since its electronic configuration in the outermost orbit n square np6 resemble with that of the inert or the noble gases, therefore it will be a noble gas element. This option is given as B. Hence mark it. Next question. The electronic configuration of an element is 1s square, 2s square, 2p6, 3s square and 3p to the power of 3. What is the atomic number of the element which is just below the above element in the periodic table? Please read the question once again. The electronic configuration of an element is 1s square, 2s square, 2p6, 3s square and 3p3. What is the atomic number of the element which is just below the above element in the periodic table? So please pause the video and mark your answer. You can even refer the table. Atomic number of the given element is 15. If you add here the powers 2 plus 2, 4, 10, 12, 15, and it belongs to the fifth group. Therefore, the atomic number of element below the above 8 element is 15 plus 18, that is equal to 33. Please mark the correct answer. Option A is the correct answer. Next question. If the atomic number of an element is 33, it will be placed in the periodic table in the four options are given. First group, option B third group, option C fifth group, and option D seventh group. Please pause the video and mark your answer. Element with Z is equal to 33. Z is equal to 33 is 1s square, 2s square, P6, 3s square, P6, D10, 4s square, and P3 lies in the fifth or the 15th group. So here option is fifth group. Please mark it. Next question. Match the oxide given in column A with its property given in column B. So table shows column A and column B, and column A is oxide Na2, Al2O3, N2O, Cl2O7, and column B is neutral, basic, acidic, and amphoteric. So you have to match the oxide given in column A with the property given in column B. This is asked in NEET 2019. So four options are given. 1 match to B, 2 match to D, and 3 match to A, and 4 match to C. Similarly, so many options are given. You have to examine it. Please pause the video and mark your answer. Meanwhile, I will give the explanation. You should remember that Na2O is a basic oxide. Hence, one should be matched to B. You should also know that Al2O3 is amphoteric. Amphoteric, that means 2 should be matched to D. 2 should be matched to D. So these two options are appearing in A as well as A only. So hence the correct answer will be A. Next question. The first ionization potential, that is potential electron volts of beryllium and boron respectively are, so we have to identify. Values are given. Option A, the first ionization potential of beryllium is 8.29 and 9.32 for boron. And similarly, option B is 9.32 and 9.32. For that is same for both the elements. And for option C is 8.29 and 8.29. And option D is 9.32 and 8.29. So you pause the video and do the calculations. I will give the explanation. First ionization potential of Be, beryllium, is greater than boron due to the following configuration. 4Be is 1s square and 2s square, and 5 beryllium is 1s square, 2s square, and 2p1. Order of attraction of electrons towards nucleus is 2s should be greater than 2p. So more amount of energy is required to remove the electron in 2s orbital in comparison to 2p. Hence, the correct answer is 9.32 and 8.29. Next question. Which one of the following ions will be smallest in size? Option A, Na plus, option B, Mg2 plus, option C, F minus, option D, O2 minus. So please mark your answer, pause the video and mark your answer. Meanwhile, I will give the analysis. Greater is the positive charge on the atom, larger will be the effectively nuclear charge. Hence, smaller is the size. So now question is which one of the following ions will be the smallest in size? So the one which has got larger charge, that is option B, has got Mg2 plus 2 positive, will have the smallest, smaller in size. Please mark it. Option B. Next question. Pauling's electronegativity values for elements are useful in predicting. So, four options are given. You have to mark the correct answer. Option A, polarity of the molecules. Option B, position in the EMF series. Option C, coordination numbers. And option D, dipole moments. So, you have to identify the answer that where the Pauling's electronegative values are useful. Please pause the video and mark the correct answer and I will give the explanation. Pauling's electronegative values for elements are useful in predicting the polarity of molecules. Pauling's scale of electronegativity was helpful in predicting one nature of bond between two atoms, the stability of bond. By calculating the difference in electronegativities, polarity of bond can be calculated. Hence, the correct answer is option A. Please mark it. Next question. The electronic configuration with highest ionization enthalpy is. This is the question asked in JEE main examination. Option A, 3s square 3p1, option B 3s square 3p2, option C Ne 3s square 3p to the power of 3. The A, B, C are prefixed by Ne. It is applicable for Ne. Option D is AR and its configuration is 3d to the power of 10, 4s square and 4p3. So which configuration has the highest ionization enthalpy? You have to answer. You have to remember. Please pause the video and mark your answer. I will give the correct answer. As we go down the group, ionization enthalpy decreases. And further, if we move from left to right, ionization enthalpy increases. Hence, the correct answer is option C. With this, we come to the conclusion of the unit 3 and the next lecture will be the new unit number 4 on chemical bonding and molecular structure. Till then, goodbye.